Assalamu alaikum. In this lecture, we will going to study about the relationship between difference operators. Remember, in our previous lecture, we have studied about the difference operators and how we have defined the different difference operators as far as our numerical methods are concerned that we're going to use in interpolation. So, first, we're going to start with some proofs. Remember from the symbols or from the previous lectures, as far as the definitions of the difference operator is concerned, we have to prove this following that you're going to see in on your screen. First one is that this forward difference operator is equal to the center difference operator, shifting operator minus 1. This is you remember this E is the symbol for shifting operator, and this is the symbol. This one is the symbol for you can say this is a symbol for forward difference operator. And then we have to gonna prove second one, that the backward difference operator will be equal to 1 minus E capital of E into inverse. This E, remember, this is the shifting operator. Then this one, I told you in our previous lecture that this is the symbol for center difference operator, that will be equal to shifting operators 1 raised to the power 1 by 2 minus E capital E minus 1 by 2. Then in the fourth one, we have to prove that mu is equal, this one is averaging operator, will be equal to half of E capital 1 by 2 plus E capital minus 1 by 2. And then again we have to prove some other thing in 5, that will be E capital E 1 by 2 plus E minus 1 by 2 into 1 plus del 1 by 2 is equal to 2 plus del. And then at the last we have to prove that E is equal to EH of D, where D is equal to D is the derivative here. Okay, I'm gonna show you in lecture that how we're gonna do this like. And then we're gonna have this one as well. HD will be equal to log 1 plus del, and that is equal to minus log 1 minus this one. This is the backward difference operator. And again 1 plus del minus 1 plus this you can say backward difference operator is equal to 1 here. So we're going to start with our first one that we're going to start here, and that is for example, if we want to define this one, remember we have to prove this one here. Actually, I'm going to show you here this thing here. So how we are taking this thing, actually how we are getting this. So these are the proofs, and these are the proofs, and these are the values of the difference or between the different two operators values that we're gonna, these are the resultant values that we're gonna use in our coming lectures as a result here. So starting with the first one, that how we're gonna have this thing. Okay, so we want to prove this thing actually. So assume that we have sorry, I'm going to start with the first one, that is here. Assume that when we want to apply when we're going to apply the forward difference operator to our function, it will going to give us fx plus h minus f of x. Okay, this is the from the definition of the forward difference operator. And you know that fx plus h when is coming from the shifting operator, so it will be equal to E f of x minus f of x. So E f of x is also equal to, when we're gonna apply this shifting operator to our function f of x, it will gonna give us fx plus h. So this will be equal to, now let's see here, this del f x will be equal to, if we're gonna put this value here, it will be equal to E minus 1 into f of x. Okay, so now see here, here we are taking this E as a common here. Okay, so that will be equal to E minus 1 f of x. From this value, you can see we are taking E as in common, and we are getting this one. And also remember that we are getting this thing when we're gonna apply shifting operator to our function f of x. This will gonna give us f of x plus h. So you see here we are doing this thing actually. Okay, so moving further, you know that this f of x will be gonna cancel with this f of x, and what we're gonna left here, that will be equal to del E minus 1, and that the thing that we have to prove here. Now moving further to our second result, that that second proof or second you can say echoid result. So again we're gonna assume something, starting with the assumption that backward difference operator, when you're gonna apply to the function f of x, it will gonna give us f of x minus f of x minus h, and from this here you see f of x will be equal to e minus 1 f of x. Now this is from this thing actually, this is we have already defined this thing, and again I have written there here as well this one. Okay, so from this thing we have written this thing. Now again taking this f of x common, we will gonna have left this thing. This is actually very similar to the first one, but only thing is that we are taking this thing actually, this definition, okay, that I am highlighting here. So that will be equal to this one, and again this now here if you get this one, from there you will get this one, and now see here this f of x will be gonna be cancelled with this f of x, and what we're gonna do here is that the backward difference operator will be equal to 1 minus capital of E minus 1. Okay, now moving on to the third one. This is the relationship as far as our you can say center difference operator is concerned. So, and we want to prove this thing actually. I'm going to show you again here so that you remember what we want to have, what we want to show as result. We want to show this thing actually. Okay, why we are getting this thing actually. Okay, so moving further, we are assuming that when we're going to apply center difference operator to a function f of x, it will going to give us f of x plus h by 2 minus f of x minus h2. Remember from the definition of the central difference operator. Now here you see it will going to, this will be equal to e 1 by 2 f of x minus e minus 1 by 2 f of x. Now see here this thing actually. Okay, and now again what we're gonna do here, we're gonna take f of x as common here, and that will be equal to e1 by 2 minus e1 by 2 here. Again f of x will gonna be cancelled with this one, and what we're gonna left here, this thing actually, and that is the thing that we have to prove in 3 actually. So we have proved this one as well. So again moving further, we're gonna move on to our fourth thing, that is the relationship as far as our averaging operator is concerned. We're going to apply averaging operator mu to our function f of x. It will going to be equal to 1 by 2 f of x plus h2 plus f of x minus h2. Again using the definition of the shifting operator from this function f of x plus h by 2, we're going to have this value. Okay, so again what we're going to do here, taking f of x common, then you have this value. Now again you will gonna cancel f of x with this f of x, and what you're gonna left here, you're gonna left this one. So this is the result, and we have defined the relationship between the central the averaging difference operator and the shifting operator. So that's the relationship actually between the averaging operator and the shifting operator. Okay, so again moving further, we're gonna move on to our fifth proof. And what we have to show here, I'm going to show you here. We're going to have to show this thing, that this one will be equal to 2 plus delta L. Okay, so moving this one, now taking this thing, please remember e capital 1 by 2 plus e minus 1 by 2 into 1 plus delta raised to the power 1 by 2. Now see here, using that definition of the forward difference operator, del is equal to e minus 1. So what we have done here, using this definition, we have written this thing actually. Okay, so this one actually. Okay, so again when you're gonna add this one with this one, that will be equal to e plus 1 here. Okay, so moving further, when you get this one, that will be equal to, actually del will be equal to e minus 1, then we have this one 1 plus del, that will be equal to 2 plus delta here. Okay, now as far as other proof are concerned, I have written down on the notes, and actually you have to do it by yourself now as far as 7th and 8th proof is concerned, as far as other relationship of the difference operator is concerned. So I'm gonna show you I want to show you one proof at the end as well, and that is the relationship of this one actually, that e is equal to e exponential h of t, where d is equal to difference derivative here, dy dx here. I'm going to show you this one, so that then the other you have to do it by yourself actually. So moving for this thing, now I'm going to show you this one actually. So this one here, okay. So from the definition of the shifting operator, we know that e f of x will be equal to this one, f of x plus h. So this will be equal to f of x plus h into f dash x plus h 2 factorial over f double derivative of f of x plus so on, okay. This is the definition of the shifting operator, and remember that from this definition we have converted this by Taylor theorem here, okay, from the Taylor theorem. So using the definition of the Taylor theorem, what we are doing here, we are writing f of, from first term as an f of x here, because first term is f of x here. Then what we are doing here, this one is basically a derivative of the function f of x, so we are writing this one as an h into d. This d basically is a derivative, showing the derivative of f of x here, capital D here, okay. So same is the case for other terms as well. The third term will be equal h square d square f of x over 2 factorial and so on, okay. Now taking f of x common, what we're gonna left here, 1 plus h capital of t plus h square d capital of d square over 2 factorial and so on. Now moving further, this f of x will gonna be cancelled with this f of x. Remember from the definition of this thing, that whole is equal to is a exponential series that will be equal to e h of t. So that is the different relationships that you have to remember as far as our difference operators are concerned. As far as other proofs are concerned, you have to solve it by yourself, and then I'm gonna give you an assignment as well, and that you have to prove that this thing, and I'm gonna upload that assignment on our open courseware page as well, okay. And I'm gonna provide you in the hint for that for that proof in our coming lecture as well, okay. So, and we're going to discuss this thing in our interactive lectures as well if you are unable to solve this thing. So this is the assignment basically that you have to do as far as our this topic is concerned. But if you find it difficult, then we're going to discuss this in our interactive session as well. So thank you so much.